think we should start. Okay? So, so in the first two CertikOS lectures, we have talked about certified abstraction layers. And we mentioned that we had a set of tools developed inside the Coq-proof assistant. Namely, we can use Coq to write those layer specifications. And we took the CompCert compiler, modified it to build a compiler called the CompCertX compiler. And we modified the C language so that these C programs can call those layer primitives. So we will get these CLiteXL layers. I mean, you can develop those C modules on top of layer L, and these modules can be written in C, or it can be written in assembly. And if you write these modules inside C, it will be compiled by this certified compiler into certified assembly layer, and then these things can be composed together. So we are not ready to use this to build a certified OS. So that's exactly what we have done. And so initially we built this sequential OS kernel. And I just want to review the problem that we try to solve. That is, we are not just doing the traditional verification of a single OS kernel and only for partial correctness property. But instead, when we say certified OS kernel, we really are saying that OS binary, a kernel binary implementation, right, a binary implemented specification, and it should satisfy many of these different properties, not just the partial correctness property or safety property, because in practice, when somebody delivers you a kernel, you are mostly interested in these other properties. In particular, lots of properties are related to security, like isolation property, which is precisely what I'm going to show you today, how we can actually prove information flow security property as a side product when we finish composing these certified kernel using layers. And we don't want to redo these verification if next year we want to prove one more property. So I guess the high-level problem is, I give you these OS kernel binary, which potentially be written in assembly, and I might want you to prove a property 1. And of course, you might have proved this property using one particular program logic or one particular certified compiler. And next year, you might be actually asked to prove another property, and so on. So, so the key idea is we don't want to redo these because nobody wants to go through the same OS kernel implementation again and again when you want to need to prove new properties. So that's why the CertikOS approach didn't focusing on like using these program logic-based approach, which we did use 10 years ago when we initially worked on this problem. But rather we care about what's the soundness proof of these program logic give you. And so instead, we basically say, let's not do that, because if we have to go through the binary and the C implementation again and again, that's a lot of work. So instead, we try to write down the high level, what we call deep functional spec for the OS kernel, or more like a fully abstract deep spec for the OS kernel. And then the formal verification become just the official verification is building these what we call certified layer with these deep spec. And then this proof can be done only once. And the critical thing is that all these other properties can be derived from the spec itself. So you don't have to redo this again and again. And of course, if you want to make this proof more compositional, you are going to break these functional spec into many, many modules. And your kernel will be probably broken into many, many little modules too. And of course, these are written in binary. That is high-level spec. So most likely, you will have a certified compiler there. You will probably directly verify C code, satisfy these specifications. But as you probably all know, that the complex system is not always done through these horizontal compositions. So in fact, you could do this, but in practice, there's also vertical compositions. Many of these specs only make sense on top of another spec. So the model of the OS itself might be actually layered, looking like these. And the code itself, OS code will also look like layered like this. And of course, these could be binary code, and they might have the corresponding C code look like this. And then when you do the proof, most likely you will be proving that this particular module implements that particular specification on top of these two layers. So this is like the high-level structure of how we reached the conclusion that we should use the certified abstraction layers. So what I'm going to do today is to spend probably 20 minutes or less to show you that one little kernel that we initially verified, give you some flavor, and then I try to show you how we actually prove the isolation property or information flow security property of these little kernels. So this is the one that we did 2.5 years ago. It's about 3,000 lines of C code and assembly. And we basically try to apply the technology I have presented so far and decompose the kernel into many different components. So this kind of a small kernel often start with the physical memory and virtual memory management, followed by some of these process management, and then there's a few other layers related to virtual machine and the syscall layer. So I want to just give you a flavor, show you what these layers look like in practice. And if you guys have time, you could go to the artifact that I mentioned in the last lecture, which is available on the web page, the PLDI 16 paper web page, and go through each of these layers yourself. So how does these things actually work? So we actually start from, so if you build a kernel, you often start with most likely look like a bare machine. So the bottom layer that we, for this particular certified kernel, we start with a layer called MBoot, which, again, just to refresh the memory, that the lowest layer here contains some abstract state and some abstract primitives. So this box basically shows you that these are the abstract state, these are the primitives that this particular layer provides. So the bottom layer, we actually have an abstract state called MInfo. This is a physical memory information table, often returned from like a BIOS or some of the low-level firmware, which tells you, which physical page is available to be used, which physical page has already been reserved by device or for special purpose. And then there's a flag called init. It's a logic flag that we introduced, which defines whether we have already called the proper bootloading process and the pre-initialization process. So this is init is a logic flag. CR3 is just an abstract CR3 register, which is used to store the start address of the page table. PE corresponds to CR0 register, essentially saying whether the paging is enabled or not. Because when we first start the machine, paging is probably off. And then at some point during the initialization, you would have to initialize the paging. Of course, before that, you have to set up the proper initialize the page table. So this ICur and iHost just specify whether currently it's in the kernel mode or not, or whether it's in the host mode or guest mode, because this kernel can be used to bootstrap Linux, and so there's a support for virtualization, hardware support for virtualizations. So these ICur and iHost are just the registers specify whether you are in the kernel mode or host mode. IPT, another logic flag, which we basically are specifying whether currently we are using the kernel page table. So this is the bottom layer, and what we do is basically start from this layer, we slowly grow the kernel code base, and at every layer we do only add a very little bit of functionalities. So for example, this MBoot layer also contains 3 primitives. So we did this is like an underlay of any code we verify. So we assume there's already some primitive called MIGet, which allow you to read the information from this MInfo, memory info, which contains a list of information telling you which range of pages are actually available for the rest of the kernel and the user code. Set CR3 is a primitive set the start address of the page table. So these are all underlay primitives. PICon, iHost set. There's a set of primitive allow you to set these abstract state bit, and there's a primitive called bootloader, which you are supposed to be called first, and after you finish this primitive call, proper of one of these init flag will become true. So the initialization function in this figure will always be marked as green. And then on top of this, the first thing I'm going to do is I'm going to prepare to implement physical memory management. So in order to do that, the overlay, I'm going to introduce some kind of an allocation table, which will be an array that it will be kind of like a bitmap or a little bit more complex than that, associated with every physical page table entry, explaining what is this physical page, whether this physical page is used or it's designed for or used for any special purpose, or whether it has been allocated or not. So this AT is actually a logical abstract state corresponds to the physical allocation table. So in the overlay, this second layer we call MATIntro Layer. We assume that you already have an abstract state AT. And there's also abstracts, so there'll also be these flags that we already see in the underlay, which we propagated to the overlay. And NPS is just a number of physical pages, which you would gather, from the MInfo and other places. And then you have these primitives at this layer. So you have an iflag set, which is inherited from the previous layer. We added these new primitives like get and set of these allocation table entries. And we also have get and set for these NPS variables. So you can see this layer really add very little functionalities. Of course, the actual formal C representation of the allocation table would probably be some kind of an array. And each array entry will map to a record A, which is two field, whether it's normal page or whether it's allocated, and the corresponding allocation table AT will be a calc map from the integer to this inductive type AT info, which will tell you whether this page is valid or undefined, and then B probably will specify whether it's allocated or not. T will specify these different usage scenario for these pages. So this is like one example of one layer that I haven't even implemented any routine on this other than give you the ability to set an entry of this array or read an entry of this array. So the cool part is that once you add this layer, any of these physical page allocation or free or deallocation routines, you are directly, the implementer no longer sees this array. They only see this finite map. And the primitive of these AT get and AT set will, do the proper, state change over these allocation table. So this is how do we add a layer that introduces the allocation table. And so on top of this, once you had the allocation table, now I add 2 layers. So first I add a layer where I'm going to actually implement a routine called MATInit. So this third layer will not do much other than I'm adding one more initialization routine called MATInit. And MATInit would simply initialize AT and NPS based on the information you gathered from this MInfo. MInfo, remember, is some data structure returned from BIOS when you boot the machine. And so from that, you can initialize the AT and NPS, tell you which page is available for you to use and which is not. And so this is what MATInit would do. And then on top of this layer, we are going to build the layer 4, which will introduce two routines, which is pfree and palloc. That basically it's going to allocate a page in high memory and free a page. And what it does is really just try to, if you need to allocate a page, you have to check the allocation table to see whether that page is available. If it is, then you will reserve it and set the bit, and free is simply clear that bit. And then on top of this, once you do that, I could actually start to add. So once we have the physical memory management, we can introduce the virtual memory. But in order to do that, I first have to introduce the two-level page table pool. So we first have to introduce a state called PT, which defines what's the current page table index. And we introduce a sequence of a page table because depending on how many user processes you would have, we will initialize, we will create a set of page table, and we call it a page table pool, and it contains 64 page table in this particular version. Of course, now we can initialize many more. This 64 is just a constant. And so this page table pool itself is an array of a page table, and the page table itself, of course, would be something more like what I showed you, two-level page tables. There's a first level page table entry. We have a primitive set PDE. We have a second level page table entries, like we have a method to do get, set, and remove. So this just shows you that in the actual implementations, the physical page table will look like this two-dimensional array, and the page directory will be one-dimensional array. And so these two data structure forms one page table. And then if you have a page table pool, of 64 of these, you just build an array of that. And the calc representation, of course, will be less implementation specific. It will have a page table pool, which will map some numbers into the page table, and each page table will map some first integers to page directory, and the page directory will contain these page table. So this is like an intermediate page table, logic page table representation corresponds to this physical ones. And we actually have an even more high level representation of this that combines these two maps. So this after you introduce these page table, then the next three layers will simply add these primitive. First, I think it added once you have these PTP page table pool, we added these page table read, remove, PT, and then we add these two initialization routine, which initialize the high memory part of all the page tables, and also initialize the low memory part of the kernel's page table, which is index 0. So each layer basically does just a tiny little bit of the things that you would have done. So, and after that, you can actually call this PTInit function, which will first initialize the kernel's page table. It will call this routine called PTInit kernel. And once kernel's page table is initialized, then you can actually set the start address of the kernel's page table into this CR3 register, because you have that set CR3 primitive. And then you can actually call enable paging, because that's the moment the machine changed from without paging to with paging. So you can see that that step as actually shifting the execution mode of the hardware. And so this routine actually requires that the initialization of the page table satisfies all the proper invariants that you need to make sure these would be satisfied before you can switch the tensor paging on. So this PTInit is the initialization, essentially initialize the calling this with tensor paging on. And then on top of this, you can actually then provide allocation for the page table allocator, because you have a page table pool, and at any single moment, you want to remember which set of page table has already been used. So you have a bitmap defining which entry of this page table pool has been used or not, and you have a proper primitives. So that wraps up, I think, for the virtual memory, management and the physical memory management. And then you basically do the same for the thread and the process management, which is about 14 layers. And the idea is kind of similar. And the point is, if you try to actually implement all these routines in, a smaller number of layers, or you try to combine them, the proof suddenly become much more complex. And most likely, if you are a student in an OS class and build a kernel following that try to combining these functionality into multiple layers, into single layers, then there will, higher likelihood you would hit some of the bugs that otherwise that would not occur if you decompose them into these fine-grained layers. So for the thread and the process management, I will go through much more quickly just to give you the flavor. And clearly, before we can talk about supporting multiple threads, multiple user process, the very first thing is you have to design this notion of a context so that you can store these machine state information or register information into each of these kernel contexts. So we maintain a pool of kernel context, and this abstract state is called PKCtxTP, which is essentially an array of kernel context where each kernel context might contain a set of entries storing registers and so on. And then on top of this, you need to support a primitive like a kernel context switch, which essentially says, well, if currently you are running some particular piece of code, you can save the current register into into a particular kernel context, and then you can load another one and into the current register. So this context switch is just a routine written in assembly, but at this moment you didn't even know how people will use this context switch, but it's it's a primitive provided at these layers. And the PCIntro would allocate a page table and a kernel context from the page table pool, and then there's also these primitive inherited from the memory management module. So on top of this, then once you had a kernel context, you actually then add these so-called thread control block pool. So this is you first introduce a list of a thread control block, and you have a set of primitives that let you read these getter and setter for these thread control block, and so on, and these other primitive. And once you have these set of thread control block, you can use them to build queues. And so you add multiple layers that allow you to define these so-called thread queue. And these thread queue, again, you have the usual in-queue, dequeue, remove queue, or getter setter for the corresponding nodes. And from these queue, you can use these thread queue will be designed to represent ready queue, sleep queue, and other type of things. Now, this queue is often implemented as a doubly linked list. So in order to actually verify the correctness of these thread queue implementations, we have to introduce sometime intermediate layers to make this proof simpler. So in the tutorial directory that we made available in the car directory on DSS 17, one of the example is precisely following this thread queue. It is taken from this thread queue examples. It turns out, proving this doubly linked list implementation of a thread queue is one of the most time-consuming verification modules in this particular kernel. So the very first version took probably 2 or 3 weeks to verify. And the proof is pretty messy. And then after a while, we cleaned up multiple times. And when we started to port this queue implementation into 8.6, just to be used for this tutorial, and it still took an experienced Coq developer, Vim, and of course Wolf, two members of our group. I would say multiple days, right, to actually get this proof going through. So it's actually a pretty good benchmark that if you have a logic, I will encourage you to look at our using the AA linked list to implement this queue and see whether you can make it better. Okay, so I'm not going to spend too much time on this because my goal today is going to focus on information flow, and I will let you guys to look through these in the tutorial. Yeah, actually, I can just briefly show you that the AA linked list in the actual C implementation is done on an array of these nodes. So we don't. So this is OS. So we don't have any physical memory allocator other than that page-based memory allocator. So if we are trying to build these smaller data structure, we actually have an array, a pretty big array of TCB, the thread control block nodes, and then this array will have every 3 nodes corresponds to 1 entry, and then one would points to one's like a previous pointer, another like a next pointer, and then the queue will point to some of these nodes, and the head of the queue will point to one of these nodes, the tail of the queue will point to some other nodes, and of course a particular queue will correspond to probably at the logic level a list of these TCB IDs, thread IDs, and then you have an additional finite map that maps these thread IDs into the corresponding TCB thread control block information, like a status of these threads. So if you want to directly verify this concrete C array implementation implements this abstract specifications, you will find that this gap is pretty big, so we have to introduce the intermediate layer that does not introduce any additional code, but this kind of bridges the gap between these two representations. So I'm not going to talk much about this because this is in the tutorial, but just show you C implementation versus the low-level spec or high-layer spec. Okay, so you see the idea that once we created these queues, then we can actually introduce something called a current thread ID. Remember, when we build these data structure, we are not using it, right? We actually don't. We can introduce as many of these data structure. Now, at some layer, we have to introduce a notion of a current thread ID, which is a global state, and in abstract state, it will be called a CID, and we will have a way to set and get this particular current thread ID. And then on top of this, once you had the notion of a current thread ID, you can actually introduce the primitive for the thread management. But most of these primitive for thread management is really just, more or less you have several queues around, and the thread spawn, kill, wake up, sleep, and yield. We are mostly just manipulating these queues, and they can be implemented fairly straightforwardly once you had those queue ready. And then on top of this, we add the IPC and introduce a bunch of these channels for IPC, and then you add these IPC implementations. So that's pretty much it for the high-level idea of how this kernel gets moved up the hierarchy. So then on top of this, we added some virtualization support so that you can have enough code to boot Linux on top. And then on top of this, we added these system call and trap handling, which you expose a set of system call to the user context. And I guess, at the high level, what we get is, even though we have this many layers, most of these layers are really, put together to serve a particular purpose. So you can imagine we have memory management, virtual memory management, thread management, process management, virtualization, and trap handling phase. And you can actually, each of these contains many sublayers, but you can compose these different modules. If you remove the virtualization layer, then you get a traditional kernel. If you add the virtualization layer, you get a hypervisor. You could add additional support, add a ring 0 process, or you can remove virtualization in the virtual memory management. You get a very bare minimum embedded kernel with no virtual memory support. So the benefit of these layers is if you are trying to verify page fault handler, which actually this shows if you execute a page fault handler in this particular kernel, what set of primitive it will invoke. And if you don't have these layers, so this picture shows, when you call the page fault handler, which primitive at which layer will be invoked. And if you don't have many of these layers, you look at the code and you try to verify the page fault handler, you will see that your view of what's going on in the state would have to shift among these many different abstraction layers. And that's why it made verification of OS kernel code particularly difficult, because at different points during the execution, you are really looking at a different set of abstract state and a concrete state. But because we divided things into layers, so then when we verify page fault handler, we can directly just only see what set of a primitive it calls. And so each, you only look at the implementation of every node directly at the layer, and so that verification is much simpler. And we could do that for every primitive it invoked, and because we are using DeepSpec, so this kind of a verification can actually be managed. And if you don't have layers, then this is, I personally think it's almost impossible. So let me move on to actually show you how we actually use this to prove the security property, which is really the main topic of today's lecture. Yes.
So, out of curiosity, the layer construction is helping you, but you also just mentioned that it does introduce some difficulty that you have quite so many embeddings calling across, for example, page fault handlers calling across primitives at so many layers.
But these are actually logic primitives. So these layers is designed here for reasoning, for verification. Many of these primitives are inlined or during the compiler, they can be inlined away.
Sure. My guess is to ask about perhaps the trade-off of possibly merging some of the layers. Would it reduce some of the complexity, or would it just introduce more complexity than it gets rid of?
It will definitely introduce more complexity for verification, right? As long as these inlining facility or inlineable primitive support in the underlying compiler is sufficiently good, then there's really no reason why you want to inlining them, because the generated code would be same. But if, for example, for whatever reason your compiler does not provide those support, sure, you could do that. And in fact, quite a few students in my group initially had the temptation of merging some of these layers, and they were always bitten by it, because usually they see that they have to pay a lot more work when they do the verification. And yeah, we had some of these layers who were developed by a particular student in our group who think that that does not require decomposition, so they try to merge these things, merge multiple layers into a single layer. Everybody else in the group hate him because that's the layer that is the hardest to maintain, and every time we have to make some change, we always get stuck at that particular layer. Yes?
As a follow-on to Stephen's question, have you measured how many cycles the page fault time would take?
We have these performance measurement in a more recent kernel, that concurrent kernel, which we mentioned. Mostly we measure IPC and a set of other micro benchmarks. So I would say it's written in C. The code is not very different from what you would have seen in the typical kernel, so we don't lose any performance. Yes?
So speaking of optimization, CompCert is not very aggressive about things like inlining or what have you. It doesn't have a lot of
Right.
optimizations in fact.
Right.
Have you tried running this on, on LLVM or GCC with a high optimization level just to see what the inlining optimization does to the performance?
We had a version of the kernel that implemented this way that can be compiled by GCC. And I don't think we ever did any measurement whether it's fast.
What the difference is because of inlining, because inlining alone should remove a lot of the overhead from.
Not really, because the majority of these primitives are not really eta regex that are calling something. It's mostly pass through. So the actual interaction is very minimum.
And some of them are very small functions that are basically just.
Yeah, but we don't have to compile them separately. We verify them separately, but when we compile them, we could compile them in the same modules, and then.
Inlining of the C code versus compiling separate functions will have a performance difference.
Sure. Yeah, but.
Never mind.
Yeah, but we didn't try to compile them separately often. We try to compile them together.
No, I'm not talking about separate compilation in multiple files. I'm saying that the inlining transformation that GCC does when it notices that a small enough function can be replaced by the code inside the function without needing to do the function call over
Sure.
that often speeds very small functions up quite.
Of course, yes. We had some, yeah, that's definitely true. And there are some of these code we noticed.
A lot of these functions are very small.
Yes, yes. But in our code, in the result, we mostly try to inline it. All right, okay. So now let's move on to talk about the information flow. All right. So, again, I guess at the very high level, I emphasized multiple times that a certified abstraction layer is very much like a verified compiler, right? If you get some message from my lecture, it turns out verifying operating system, at least in our project, right, is more like verifying compiler. Not just like a CompCert way of verifying a whole compiler, but we are trying to verify a compositional compiler. So you guys have heard that if you proved some security property at the Java level and you want to make sure that the generated code, assembly code, would still be secure, then you ideally want that compiler to be fully abstract or the kind of, does not introduce any side channels and additional information. And the fact we are using deep specifications, the fact that we are really proving each of these certified abstraction layer really are connecting, showing the spec and the underlying code really have no gap, give us the kind of a full abstraction that we need in order to propagate the security property we had at the high level down to the generated code. So I guess I will first start that just to try to motivate what we are trying to get, because the OS kernel, one of the main application of the OS kernel in modern application is to use them as a partition kernel, also called try to divide machine resources as multiple partitions and try to show that code running in one process cannot influence code running in another process. And there's many such examples. There's web browsers, there's a hypervisor when you have multiple virtual machines, and even in the distributed system, you probably also want this kind of some of these isolation properties. So the general goal is to what we are trying to do is to formally prove an end-to-end information flow policy that actually applies to the low-level code of these systems, including the OS kernel. So what are the challenges? It turns out that even just to specify this policy is already pretty challenging. There's lots of paper in this field, but how do you actually specify these policies is kind of unknown. At least there's multiple approaches, and it's not clear which one is better than another. So what we really want, ideally, is we want to specify these high-level policies, right, at a very high-level abstraction. Because when somebody say, hey, I'm running these different processes on top of this OS, I don't want to know how OS is implemented. I just want to know that I have these different processes and there's a specific policy. Certain kind of a communication is allowed, but a certain other kind is not allowed. Or maybe they are not allowed to have any communications. And if you want to allow some specific flow, then it's really some form of declassifications. So that's one of the challenges, how to specify. The second challenge, of course, is most of those system code is written in C and assembly. And if you try to verify these low-level assembly code, and then maybe you verified something in C, and you also have to deal with the compilation. So this diagram is just showing you that if you, even with a verified OS or verified compiler, how do you actually, verify this whole thing satisfies some particular security property? It's very challenging, right? You pretty much have to do some of the verification we have already described, but even with that, it's not clear how you would want to do it. And even if you use the CompCert is not known to preserve security properties. So how do you make sure it actually, preserves security properties? So, so the next question is even the problem of verifying security property at the C level is hard. We have a lot of work in the community, such as GIF, right, which talk about developing new secure type system, and it's only mostly applicable to type-safe languages. And we are not aware of a really good type system or program logic for reasoning about C, right, or weakly typed language. And then all of these, even with these type systems, secure type system like GIF, the classification is always a very, problematic case for these security type system. And then, in fact, sometimes many of the code you try to verify, you will find that these low-level code actually have internal leaks. So it's impossible to prove they are secure using the labels. You might have internal leaks, but these leaks are internal. And they will never leak to the, externally. As long as you sandbox the whole thing, then the whole system is still safe. So, and then on top of this, after you prove the security for all components, you have to somehow link them together to get a system-wide guarantee, right? So if you take the view that I'm actually going to verify the security of every single layer or every single component in a complex system like OS kernel, that's kind of a fairly daunting and almost, unrealistic. And at least it's probably not going to work using the traditional whole logic-based approach. So clearly none of these existing systems can actually solve all these challenges. I just want to mention that, for the related work, there's, of course, lots of work on using security labels, right? But these, like GIF and Flow, Camel, and the many other things. And They can be applied to typed language, but there's no formal end-to-end guarantee. There's also dynamic label tracking and label checks work. Mostly these runtime, there's often, because it's a runtime dynamic label tracking, so it often introduces execution overhead, and it's mostly, when you deal with declassification, it becomes problematic, and the runtime exception often can leak informations. And then, of course, there's the SEL4 work, which is also, they provide end-to-end security proof, but that proof does not support anything about assembly code, and in our work, we actually show that there are these places in assembly code that could potentially become security side channels. And then the SEL4's verification is with respect to C-level machine model. So it ignores many of the intricacies of the low-level virtual memory, address translation, page fault handler, and the context switching. And then the compiler is, there's no guarantee that the C compiler maintains security. So the work I'm talking about here was the first published in PLDI 16 by my student David Costanzo. And so we basically say we can solve all of these challenges with a single and general methodologies. So I will, in the rest of this talk, I will basically show you how this methodology works. So we actually provide new ways to specify, prove, and also propagate these security policies with a single unifying mechanism, which we call observation function. And the observation function is so nice that it happens to be inside with something you would have defined anyway if you are talking about the abstraction layers. So I will explain what this observation function is. So it turns out, if you want to describe a sophisticated security policy with declassification in it, you have to go beyond the classical non-interference theorem. And how do you specify such declassification policy? We argue that observation function is one of the really great way specify these declassification policy. And furthermore, you still get a very nice non-interference theorem, even though you have declassifications. So that's something I want to show you. The second is that with this observation function, we can actually use the simulation proof or refinement proof that I have showed you before. You can use that proof to prove some of these security properties. In fact, often, when we talk about verifying information flow security, our mind is always thinking about, I need these security labels. Some are marked with high security, some are labeled with low security. And you have to do these label-based reasoning. But in programming language, one of the most common technique to prove security is actually information hiding. So we have found that information hiding is very, very important when you want to prove OS security. And information hiding really means that there are leaks locally, but nobody cares because it's all encapsulated. So virtual memory is a very good example because if you have a two-user process, we try to show that these two-user process is isolated from one another, and regardless, whether this other user process, how they react, how they, whether they change its execution behavior, I want to show that is not going to influence my behavior, my current process's behavior, and you can almost show that under different scenarios, because you have another process running, my process will clearly be executed with different page tables because the kind of physical page that are allocated to my process might change depending on whether there's other user process running and how aggressive this other, physical other process is, interleaved with my current process. And so if you want to really prove that my behavior is still, not influenced by this other process, the only way you could do is to hide the fact that, the fact that which physical page you are using. So the information hiding basically says, well, if you can show that your user process behavior is, equivalent to running inside a virtual memory or virtual space with only your virtual address and independent of which physical page it's allocated to, then that's totally okay. It does not matter which physical page gets mapped to your virtual page. So that's the type of things that this kind of information hiding play a more significant roles. And the idea of using this observation function actually allow you to unify these two types of proofs. And then the third thing is that we can prove some property, security property at the specification level, and then we can actually introduce the notion of a security preserving simulation and a security preserving compilation to propagate the property we have proved at the specification level down to the, either the lowest level of the kernel or to the assembly level. So I will talk about this methodology, and then I will also briefly talk about how we actually apply this methodology to the CertikOS that I just showed you. And so this particular work is fairly complete, and that's why we made the artifact available, and so you guys can actually download and check out all these proofs. So we managed to prove some form of oscillation properties. We actually found multiple bugs. I will explain what those bugs are. And the policy that we verified is the user process running over CertikOS cannot influence each other in any way if IPC is disabled. But the idea, we could actually prove richer policies. So I want to briefly mention the history that we didn't arrive the current approach immediately. In fact, my student David Costanzo spent many years of developing separation logics extended with the information flow labels, try to verify these low-level code. So for 2 or 3 years, we have been working on that approach. We developed the security-aware program logic. We extended it with these labels, and then eventually we find it does not work. So we have to switch to the current methodologies. So I just want to show you why program logic-based approach have some serious issues. So here's a piece of code. I don't know how many of you can see it, but it's basically saying I have an array of 64 entry, and you can view this as probably a calendar. And this array A as the base address, I is initially 0, and I'm running a loop. And I'm scanning through this array, and if I find entry, calendar entry that is not reserved, that is, if this x equals 0, then I will print out that first available entry. Otherwise, I will skip and then keep looping. So this process will essentially print out all the available empty slots in this calendar. So this is like some low-level code, and you could develop a separation logic, a whole triple, PCQ, and the soundness proof can be made, you can say that if precondition P holds, then C does not crash, and C always takes P states into Q states. That is, if P holds, C will not crash. When C finishes, the resulting state will satisfy Q, and you can actually extend the soundness proof so that say, oh, C also satisfies some security policy specified by P. And the security policy, you can describe, these P's can be actually made into described labels. So in order to design the program logic, we would probably first, develop these languages, and on top of them, we will introduce some of the pre-post conditions using separation logic. So this precondition will say that, this array actually it's a separation logic conjunctions, and each of the entry contains some values ni, and a label li, and it basically says if this entry of array entry is not equal to 0, then the label attached with this value is high, and if this entry is 0, then this the label for this 0 value is low. So this is like already conditional labels, and from that you can actually prove that use this particular logic that this policy that actually holds, and you can prove some form of properties, security policy.
Questions regarding what restrictions are there. So are you, one question is, are you allowed to branch on high variables? On variables?
So this is the approach I'm trying to say it does not work. This is the approach that I try to say it does not work. And unless you have a particular interest.
Maybe not for this one, but for the current one that you have.
Yes, we will have those kind of examples. Maybe you can ask me later when I.
Also, I mean, whether like in all of these approaches, you're allowed to change the label attached to a variable throughout your program or not.
So right now we don't attach any labels. So in the current approach, we don't attach any labels. This one is just show you our initial failed attempt that we try to attach things with the labels, and why this problem is we eventually abandoned this approach. So the problem with this approach is, of course, first it's language specific. It's bound to C-level reasoning and control flow constructs. And it depends on specific code detail. Any change in the system code would require some re-verification, right? And it overlaps the functional correctness proof with security concerns, which is a kind of bad. And it's, when you designing code, it's hard to think both about correctness proof and the information flow proof. And actually, more importantly, it's kind of wrong to keep thinking about the information flow if this piece of code is simply going to be encapsulated inside the sandbox. So any leak between these high and low security variables may not matter anyway. And so if you use this logic, you probably cannot prove a certain program being secure because they are insecure anyway. And the fact that they are okay is because in the bigger picture of the large system, those leak is temporary and nobody really care about them, or they are encapsulated. So the ideal solution we want, yes?
I don't see why you have to reason about functional correctness along with security.
Oh, I'm just saying when you use a single program logic, just like what I showed you in previous slides as a whole logic, then this particular work we did, maybe not your work, following the traditional program logic with the pre-post condition, and then you attach data with labels, will involve, you are essentially using this verification to deduce both the functional correctness and some security properties.
Is what you're saying you will have some extra information in your pre-proof conditions, but you could ignore that, right?
But the very reason you attached it is you want to prove some property about it, right? If you don't prove it, then why you attach it? You should not have attached it in the first place. But I think you are now arguing with a particular work we considered as a failure. So maybe you can ask the question about the current work, right? So the ideal solution would be, instead of going through, line by line reasoning about the secure information flow, you want to write down the high-level specification, right? You want to abstract and try to say, hey, what is this piece of code the corresponding high-level specification is like, and you prove that the spec is secure, okay? And then you try to show that all code that implements that spec is secure, and then from these, you can deduce that C is also secure. That's the ideal solutions. And of course, there's lots of things we have to make it precise. So the very point of this work is to show that this ideal solution can actually be achieved if you have a certified kernel like what we built before with the certified abstraction layers. It turns out that we can introduce some notion of an observation function, and that observation function will be simultaneously used to define security policy, and then it can also be used to prove that the high-level operating system called spec indeed is secure with respect to this security policy, and then you have a security preserving simulations, and you can deduce from the fact that high-level system called spec is secure, plus the security preserving simulation and the whole execution behavior, you can show that the end-to-end guarantee at the assembly level, at the machine code level. So that's the kind of things that I'm trying to show you in the next 30 minutes. All right, so how do we specify and prove security? So as I mentioned, that ideally I want to, from the high-level specification, I want to show that the spec is secure. So everybody here probably already knows that the most common way of defining security is using so-called non-interference. And of course, the pure non-interference is actually fairly easy to understand. It's basically saying Alice, so if I have two processes, Alice and Bob, we're essentially saying Alice's behavior is influenced only by her own data. So for pure non-interference, if you have a two machine configuration, Alice Bob 2 and Alice Bob 1, and because Alice's data is the same in these two configurations, when you execute your program, then the resulting configuration, the Alice state will be same, even the Bob state clearly could be different. So this is what we normally know as a pure non-interference. And so this is actually often what typical theorem you see when you use security label-based reasoning. However, as I mentioned, that in practice, almost every interesting security policy will involve some form of declassifications. So how do we specify those more complex policies? So here's one example that you might want to declassify something, but not everything. So imagine you have an employee salary database, and here's a function called print average, which we will say that the employee's salary is actually private, and so we don't want to let other people read the salary numbers, but average salary is public. So here is an example that a particular kind of security policy that this print average is clearly still secure with that particular security policy, because what the print average does is going to go through the database, add the sum, does the average, and then print out the average. And this code clearly will be, bad if you use the labels, because, anything calculated from high data will be high. So how do you want to verify, describe this kind of things? And of course, the calendar example I mentioned is another thing. If Alice wants to schedule a meeting with Bob, and here's Bob's private calendar, and Bob would say, my calendar is private, but anybody or Alice can see only whether a day is free or not free. Alice cannot see if the actual data inside the entry if it's not free. So if we want to write a scheduling function, Alice wants to execute this scheduling function going through this calendar. So this code might say that, okay, I'm going through this calendar array one by one, and until I see an entry that is empty, and if it's empty, then I can choose that particular day and then assign that particular event into this entry. Otherwise, I will keep looping. So this is a valid schedule function that would match the kind of a desirable policy that, what I just stated, that Bob says, Alice can schedule something, but you cannot read what is already scheduled. So these, all these things, if you want to go fancy, you often need conditional labels, dependent labels, and so on. But things get, complex. So the generalized non-interference basically says, well, let's try to introduce the notion of observation. Instead of saying Alice's behavior is influenced only by her own data, we will say Alice's behavior is influenced only by her own observations. So given a state sigma 1, Alice's observation will be called zeta A. It's a semantic function maps any state to some data. And so if you are given two states and you have a particular observation function for Alice, then the generalized non-interference theorem would say that if Alice, the observation of the initial state are equivalent, then this function is secure if executing it over both configurations will lead to these two resulting configurations, sigma 1 prime and sigma 2 prime, and on those two resulting configurations, Alice's observation is still identical. It's still same, yes.
Are your final proofs going to include any observation functions that capture time somehow?
Not in this proof, but there's a work in progress that try to deal with the timing side channel. Yes. So this is the notion of a generalized non-interference. And so what this zeta is? Well, it takes the principal, like Alice, and program state and generate a observation. And that observation can be any type. So if we have a state transition function, let's say S is a step function that goes from one program state to another program state, you could say, or S is a specification, right, describing a transition from one program state to another state. Then we say this specification S is secure for principal P if this particular generalized non-interference property holds. What it says? Well, it says given any of the initial state sigma 1, sigma 2, if the observation of this principal P over sigma 1 and sigma 2 is the same, and this particular specification S is going to take a sigma 1 transition to sigma 1 prime, and it will take sigma 2 transition to sigma 2 prime, then the resulting, for these two resulting states, the observation by principal P is still identical, is still same. That's the generalized non-interference. So now we can actually see how it would work. So this clearly generalizes the notion, of a regular notion of security labels, right? So here's an example that suppose you have labeled a state where I have variable w, x, y, z, and x, these are properly labeled. This w has 5 and is labeled by A, and x is 17 labeled by AB, and suppose these AB are Alice and Bob with these lattice hierarchies. And suppose I'm Alice and currently, so zeta A is the observation function of Alice over these traditional security labeled model will clearly say, well, W is clearly observable, but not this X, because X, in order to read this, it also requires you have you have B. So this is hidden. Y is owned by B. Clearly, Alice cannot observe it, but Z is public, so Z can actually observe it. Yes?
So you're assuming your specifications are deterministic?
In most of our work, all these specifications, yeah, deterministic.
Since otherwise the properties.
Sure, I understand what you mean. Yeah. So now we can see that the average salary, the observation of a state is, employee salary is probably private, but Alice can observe the average salary. And so you can actually have two salary database whose value are different, but their average salary will be same. And now you can actually prove that the particular print average function I show you is a refinement or simulation of this print average spec. what this print average spec does is take a state sigma, and it will, what it does, well, it will basically just says, let's say this state will contain an output buffer. So it will append a new average value of all the salary inside this state sigma, and print that average value onto the output buffer. And so the observation function sigma A will be just the, given a sigma, the observation function will be the average of all the salary and the output buffer. So if you take this sigma A, then you can actually show that this print average is secure with respect to this observation sigma A. And so this sigma A is served on the one end as a security policy saying what is observable, meaning what is declassified to the public. And at the same time, you use this actually to define what do we mean by a primitive is secure. Okay? We can do the same for the calendar examples. So now Alice can see only whether a day is free or not free, but not the content of the Bob's calendar. So we could define the actual observation function as just thing that hide all these content, but just give you a Boolean flag saying whether this calendar entry is free or not free. Green means free, red means not free. And now the schedule function that I just mentioned before can actually be shown to implement a schedule spec, which this spec basically says, given any state, it will return some of the calendar entries if this F is actually free inside the Bob's calendar, or if none of the entries is free, then it will return none. And so the observation function, of course, is just what I described, that if this entry is free, it will return none. If this entry I is none, then it will return Boolean true, meaning it's free, otherwise it's return false. So using this kind of observation function, you can also prove this particular schedule function or this particular policy sched spec is secure. So you decompose the verification of security of this piece of code into a simulation proof plus the security of this spec, these two proof obligations. So once again, you can show that generalized non-interference for this spec is secure. So more interestingly, this is the example I just mentioned at the a few minutes back when we look at the virtual memory address translation. So there's a abstract primitive called VA load, which essentially takes a virtual address VA and takes the state sigma, and so this is actually VA is the page. Let's see. This VA is actually the map to the it's a virtual address, and so what this does? Well, take the virtual address and go to find the thread page table pool inside this state. And if this particular virtual address corresponding to a page directory that's valid, and you can find a page table entry, then you use this virtual address to index this page table E and see whether there's a valid map for this particular virtual address. If there is a valid physical page, then we are going to load the actual content, the actual page number, right, from the physical page number multiply page size, virtual address mode the page size, so you just get the actual physical address, and you search this through the HP, means the physical page of this state sigma, and then you can load this data into the register RD. If the page is not present, you will execute the page fault handlers. So this is like a VA load primitive spec. And you can see that this physical page clearly is a kind of a confidential. Because if you, page table, physical page is not something that a user process is supposed to see. And if you treat these in a regular label-based model, you might set them as high security. And then clearly this wouldn't be secure. This would be highly secure, so you cannot declassify it. So what I'm trying to say is if you look at what's going on, there's a really insecure component or highly confidential component used to implement a primitive that's actually considered as secure. And so there's some declassification going on. But what's really going on is that we use the information hiding, right? We use the abstraction function saying, yes, even though the implementation of a virtual memory load did go through these page tables that probably have these highly confidential physical page number in it, but from the user process point of view, those are not observable. All the user process observable is just a map from the virtual address to the content of this virtual address, what maps to. Regardless how this virtual address actually gets mapped to specific physical address, as long as it implements this proper virtual memory image, then everything is all set. And indeed, this is what's observable by the user process, not the underlying physical page numbers. And that's how we manage to avoid proving the security of this code. And because because we hide all those things, and this particular observation function, we can actually show that with this observation function, we can show that the proper VA load function is actually secure, with respect to this observation function. Yeah. The person who want to prove security properties. Yes.
How does this work when new pages are being allocated on demand?
So usually there's a container mechanism that bounds the number of pages you can allocate. So you can't. Is that what you have in mind?
This function seems to consider sigma and therefore the page mapping to be fixed, but in reality it will change as more memory is needed by the process, right?
Yeah.
So how does that get modeled here?
Oh, it can be, sigma is not fixed. I mean, sigma is sigma is the whole state. So inside there's a page table in it. And so you can actually add these, you could potentially execute a page fault handler, and that would add new entry into this map, and it's still okay.
What about leaking information based on having run out of memory?
So that's what I mean by container. So every process will assign a quarter, and so you can, if you exceed that quarter, then yes, your code will not run, but it would not influence another guy's behaviors. All right. So after we talk about how do we specify and prove, proving security property at the spec level, then I can talk briefly about how do we propagating security across simulations. So this is a step where if you prove the spec is secure, how do you show all code implementing spec is secure? It turns out not every simulation is secure. So if you naively use the simulation that I just mentioned in our previous lectures, they are not secure. So here's the example. At the high level, you may very well implement a swap that swap two variables, x and y, and they will, you have two variables, x and y, 17 and 42, and the swap spec will say, after this, x get 42, y get 17. At the low level, in the implementation, you may very well have a machine n that you use the temporary z and to store these the temporary data. And if these values are actually secure, then you accidentally left some information inside this z. So So if you are proving simulation R, you know, most likely you don't talk about Z. You are just saying, oh, this machine simulates about the upper one as long as the X value in both machines is the same and the Y value in both machines is the same. So you can actually prove these simulations without worrying how the value Z is changed. But if this value Z is actually being used, they might actually become a problem. So when you actually try to prove security, you have to deal with these cases. And so the idea of how do you propagate in security is you have to define observation function for every machine. So if you have a sigma, so for machine M, you will have a zeta M. For machine N, we will have zeta N. And then you have to make sure that this simulation is security preserving. By security preserving, we really just means that if you guys are finding that abstract function or simulation relation R, you have to make sure that if, you know, you have to satisfy these properties, that you are relating a high-level state sigma 1 and a sigma 2, right? A low-level state sigma 1 with a high-level state, a high-level state sigma 1 with a low-level state S1, and you are relating a high-level state sigma 2 with a low-level state S2, right? If, for example, your observation at the high level of these sigma 1 and sigma 2 is equivalent, you have the same observation, then I have to guarantee that the observation at the low level has to be same. So this is basically saying, you know, you can't just magically introduce some difference when you connect these machines. What is considered as observationally equal should be implied by the observation that you made at the high level if you ever try to create this kind of a simulation between two machines. So actually, this is one of the main ingredients, new requirement imposed on all these 37 layers when we prove these properties. And there's another ingredient in order to describe the kind of a whole security theorem you need from the single step. What I showed you is how do we prove the security property of every single primitives in the system. You actually also, at the whole machine level, you need to say that the kind of a non-interference theorem is not just a single step. You want to say that if given two initial state sigma 1 and sigma 2 and Alice's observation is equal, I want to say that then these two machines can all execute, you know, in the same way. So I'm looking for a map called BA, which says, given me an initial state sigma, what would be the behavior of this whole, the rest of the program? And so this BA sigma is very much like the kind of a behavior CompCert uses, like, you know, whether this program will terminate, or it will go diverge, or it will crash, or it will, reactive infinite loop, but in a reactive way. So ideally, the whole machine security theorem will say, if these two observations are equal, then the behavior ideally will be equivalent in a certain way. And in order to do this proof, we have to impose some requirement of some notion of a monotonic properties. This is kind of related to the idea that you can't erase observable events. That is, at any moment you observe this set of events. When you keep executing, you cannot erase what you already observed. Instead, what's observable has to be monotonically increasing. If you don't have that property, then there's some problem. So this is the end-to-end security property that we could potentially prove. So we first prove the security property of every single system call at the specification level. And most likely that will be based on the observation function zeta s for every principal p. And at the implementation level, of course, we have another observation zeta I p. And zeta IP is monotonic, and we want to we assume I is already security preserving, It's a security preserving simulation. And then from the generalized non-interference of every primitive at that spec level, so this is just generalized non-interference for the security property of a high-level spec primitive. Then from that, we can actually show that given two high-level state sigma 1, sigma 2, right? And if the P's observation is equal, and this high-level state corresponds to some low-level state S1 and S2, then the machine execution of executing the whole machine on top of this low-level state observable by P will be equal to the behavior of executing the machine started from low-level state S2 observable by principal P, and these two things will be equivalent. So that's what we mean by end-to-end security. So we could actually apply this to the CertikOS proof. I just want to briefly go through that. This particular kernel we proved has 32 layers. We didn't include the, I think, virtual machine virtualization modules. It's about 354 lines of assembly, 3,000 lines of C. CompCert compiled those C to assembly. Every layer has primitives that can be called atomically. Bottom layer is the MBoot. Top layer is the T-sys call, which contain 9 system call. Here, the system call is more general, so we include initialization, virtual memory load, store, page fault, memory quarter, spawn child, yield, and print. And so you actually have to define a notion of observation function. The observation function for process P in CertikOS, for example, will be those registers if P is currently executing. If you are not executing, you cannot see the current registers. The output buffer of P, the current process P. The function from P's virtual address to values, that's really just the P's virtual memory image that does not contain the physical memory. P's available memory remaining quarter, and the number of children P has spawned, and the saved register context of the process P, the spawned status and the currently executing status of P. And so we actually can prove the security property, which look just like what we showed before. So in the paper, there's a detailed evaluation of how many lines of proof this corresponds. Actually, the security proof is fairly short compared with the actual CertikOS proof because we did it directly on the spec, and the actual effort took about 6 months. I just want to show you when some of these bugs we found. For example, the initial version had precisely the problem Adam asked about. So if you don't have the container mechanism, then you can have Alice basically says, I'm going to spawn a new process and then call the yield and let Bob execute. Bob have a secret value 42, and then Bob will spawn exactly that many number of 42 42 process and then yield. And then on this side, I can spawn another process, Alice, and just to do based on the process ID, I can get that secret values. So this is, of course, side channels, and that's should not be done. That is, so in order to fix this, we have to introduce some kind of restrictions on how many child process you can spawn. So for example, so this is you have to bound the maximum number of children you can spawn. So for example, this would be a tree of the process hierarchy that only allows 3 children. If you bounded this, then you will never be able to use this to convey these pass values from one to another.
Another way to fix this would be instead of having one single thread pool where you put all the same thread to split every different thread pool per process within the network.
That would work, but that already assume you have 2 levels. So at the top level, you still need a process pool, right? And then for each process, you are saying you can schedule some different thread.
I think it would be similar to what you do like in the case, just like with physical memory, where all the actual physical memory of all the processes in the same bucket, let's say. But then the virtual memory kind of provides the abstraction. You could imagine the same doing the same.
Sure. Yeah. Okay, so just to wrap up, yeah.
Did you find that error because something broke in your proof?
There's actually, yeah, quite a few places where things cannot be proven. And so the paper, PLDI paper, contain a few examples, additional examples, what we discovered. Yeah. And some are actually in the assembly context switch implementation code.
So you applied this to a small version of CertikOS. Is there any reason why it would be hard to scale this to the existing version of CertikOS, or is it just a matter of time?
There are actually new challenges. So if you are talking about the current concurrent version, dealing with the concurrency is one major challenge, because once you had a concurrency, it's not even clear what non-interference means. Like David asked that whether all the function is deterministic. Once you had a concurrency, there's actually non-determinism going on. So what would be the corresponding non-interference theorem, when you modify into if you modify in two processes the values, then maybe the interleaving will change, and so what would be the?
I have a conservative one saying none of the parallel paths would interfere or something.
Sure, but once you have concurrency for the concurrent code, you have to define the security property carefully, and it's not always easy. I mean, at least it's a well-known open problem in the community. I'm not saying our technique wouldn't work, but nobody have tried that yet.
So concurrency is like the main challenge for.
It's the main technical challenge, but there's a lots of other challenges that I didn't talk about. More engineering-related challenge. For example, the fidelity of the machine model. It turns out the current CertikOS can only verify all the way to the assembly language with the composite memory model, but composite memory model is block-based. It's not a linear memory model. And because it's not a linear memory model, so the user address space because user address space using virtual memory is linear, so there's some gap there where how do we actually reason about, so we don't have a very rich machine model for reason about the user address space code, because I guess the high-level point is we really want to model a faithful user-level machine, so that even if it has bus error, even if it has some call dump or these illegal instructions, it will be still considered as executed safely because it will trap to the kernel. Kernel will do some work, and right now our machine model does not have that level of detail, and simply assume the user-level code will be safe. But that notion of safety is too rigid. But if you have a richer model, then you would be able to model those. And of course, there's these other instructions like RDTAC related to the timing channel, which we have to address. So define a user-level machine model for user instruction. But then even the end-to-end security theorem I was mentioned before, I think Adam asked the question that, if the security policy has to be based on this observation function, what if your observation function is wrong, right? And the oscillation property of a two-user process ideally should not depend on any particular observation function. What you really want is that I'm going to bootstrap the machine. I see the initialization code. I just want to show that when the machine bootstrap, and then the state of this process will actually, will automatically satisfy will be secure. Once we get to a point, you can show that the proper invariance holds, and it will lead into the sum of the initial condition that are required by these hypothesis of this security theorem. But overall, the point is, if I give you all the initialization code and the kernel code, then I don't really need the observation function. I just need prove a theorem that says define spawn P, process P was just spawned by the kernel, and then we will say for any two processes spawned by the kernel, then you know, the observation function under these two different state sigma 1 and sigma 2 you know, will be same. That is, regardless, you know, what are these state sigma 1 and sigma 2 is, their behavior will always not be influenced by others. So this kind of oscillation theorem will be independent of the observation functions. Okay, I guess I will stop here, and tomorrow I will talk a little bit more about how we deal with the concurrencies. All right?
Okay, quick announcement. As announced earlier, we'll have a not too long discussion for those that are interested about contributing to the state of documentation. Take 5 minutes to get some water and use the bathroom or whatever, and we'll be back in the front part of the room.
Hey.
Question.
Yeah.
First is, you of course trust theta S to be correctly specified. Is there a proof obligation that is unprovable if you misspecify theta I? For example, if the developer accidentally specifies theta I to always be the empty set of observations, is there something that goes wrong?
Nothing will go wrong. I think you
Also,
have
so the specification of observations at every one of the 37 layers must be trusted.
No, I mean, clearly you don't
Something
need.
must go wrong if you specify that the observation at the machine level is empty.
Well, if you say the machine level is right, so you have to specify those. You have to. I mean, the proof already shows these observations is consistent with each other because simulation already shows that. You know, the top level observation, because you don't really care about what the intermediate layer is, right? You can compose everything,
So,
view the thing
I
as
only
a
care about, my
right.
only question is the bottom.
Right.
If I specify that my observation at the bottom is
Right.
always the empty observation,
Right,
there's nothing that's observable at the bottom machine level,
right.
what proof obligation goes wrong?
Oh, then you cannot prove the top one if the top level observation is not empty.
But the only proof obligation you showed as a requirement for proving security was proving bottom top to down, so S to I. None of the proofs that you show or theorems you showed required proving I up to S. Is that somewhere like
Well,
not shown?
no, it's well, the theorem we prove. We are proving the security. We are propagating. You know, the security property we proved about the spec to the whole machine.
Sure.
And
But there was an implication, if you look at the theorem, you said you require that, so that is the security property.
simulation, right?
Yeah, if you go back a couple more slides, this one, yeah, so the thing in the box,
No, that's just the high-level security properties. I think what you mean is
somewhere.
no, you mean this R is a security preserving simulation. That's what this R
Yeah,
says.
maybe that's what's going on.
Right. R says that
R is parameterized by theta.
R is yeah. You should view that this observation is actually part of the layer definitions, because every layer should have an observation function attached with it. And so when we say R is a security preserving simulation, it should.
There's no way, like, just follow up like this.
Right.
Checksum on this.
Yeah.
There should be no way for me to screw up theta I.
Yeah. There's no way you can screw up because it has to be implied from zeta S.
Well, it could be monotonic, but it could always report the empty set of observations. That is a monotonic screw up.
Monotonic is a. Let's not use the word monotonic here for the moment.
There.
Oh, it's something totally different. It means, yeah.
So maybe a final question. What is the output buffer?
Oh, it's just, you know, we try to use this as a way to describe what is globally observable. You know, it's a print. It's just print
Right,
something
like
to the
stand
screen.
it out, or I see.
Yeah. It's just the simple things.
All right, yeah.
Don't go away, you guys. I have a question that may cross boundaries here.
Okay.
So this is very pretty.
Okay.
A different thing, but may have some relationship, is shared fate with respect to failures. So, not uncommon, I want to implement something where I have backup, and if one part fails, then the other part doesn't. But let's say I'm buying communication lines, and I want to buy distinct communication lines, and that's the contract that I get with the supplier. And then time passes, but the supplier finds that it's easier to supply the two functions over the same shared channel. And I don't find out until something breaks, in which case they both break together. How do you process? How do you force a condition that could be implemented all the way down that would keep these things separate?
I mean, overall, I don't know. I feel like the work they are doing is really also try to show that with the crash recovery routine, they implement a high-level abstraction that says, things even with these crash recovery, they are essentially prove some of these high-level operations are atomic in the sense that either it's identity, or if after recovery routine is done, it did the atomic work, or it didn't, right? So
there's a relationship between the independence and the isolation.
Okay.
We didn't really do anything with independence.
And even in the real world, you have to own the infrastructure if you really want some independence guarantee or fault
A
independence.
result that's slightly related to that, not about networks, but about something else.
I'm sorry.
I can tell you about a result related to what you described, not about networks, but about something else. But I want to make a remark.
Okay.
So,
Thank you.
another solution to your process ID problem is to randomize the process ID.
Okay.
Okay? But then all hell breaks loose in your...
Right. You bring in all the probabilistic reasoning
And we
too.
need to use the foundational cryptography framework to do
Okay.
the proofs.
Okay. Is that what is the people do in the
More
practice?
reasonable solutions are hierarchical process IDs that are local.
The point is that
Sure. Yes.
proof methods
That makes sense.
at the
Yes.
Galena level rely on that it's deterministic.
Correct, no, I know.
And so,
Well, there's these various tricks to treat cryptographic failures as non-termination.
Aha.
that's not what I mean. I'm just saying that when we do crypto proofs about Galena functions, which we do in the HMAC and
Yeah.
Stephen, it gets very heavyweight. Because it's not so much about the crypto, it's about the computational monad over probability space.
Yes. Okay. Hi.
I have a question. So, in your generalized non-interference
Yeah.
theorem, so this
Yeah.
is progress insensitive. Because you both assume that both machine steps, right? Sigma 1 and sigma 2 both steps.
In our actual calc implementation, it is termination sensitive.
Right, because you need that when you add concurrency.
Yes.
Otherwise you will continue.
Yes.
And so then I was wondering, what do you do about like inter-process communication?
It turns out that basically once you had inter-process communication. Oh shit.
And since your voice is loud,
I don't really need it, right?
you don't need it, but also we're going to fire up this next conversation over on the other side.
I should move away. Okay.
So I suggest taking your conversations.
Okay, we can talk.
We do have a Freud from yes, we all have
Also, I think that can work here. But there's another one that's posted links to right now.
So I thought about that.
seats kind of over here. Okay, although if people want to sit way in the back, that's also fine. All right, so let's have a little talk about helping improve documentation. There's been a whole bunch of discussion on the Slack channel and in the real world about things that one might do, and I have learned a lot in the past couple of days. So my thinking about these things has evolved a little bit, and I want to briefly summarize some of the things that I think I now know. One is, there was a lot of back and forth the other day about whether contributing to the Coq wiki or having a new wiki or something like that would be a good idea. And some people were pro and some were con, and I was kind of undecided. I have now had a careful look at the Coq wiki, and I am con.